Hello, in this video we're going to look at volumes for square cross sections where we have actually two different regions we need to look at. So we won't be able to set up a single integral to solve the problem. We'll have to set up multiple integrals to solve the problem. So we had the camera. You can see a problem right here. The base of a volume which has square cross sections perpendicular to the y-axis is bounded by y equals x squared, x equals 1, and the x-axis. Calculate the volume. So first of all, let's draw the region. So here is the region. It looks something like this. Here's the curve going like that. And the problem is we're looking at a region that is something similar to this, okay? Now, if the problem had said, instead of that they are perpendicular to the y-axis, if the problem had originally stated that they're perpendicular to the x-axis, this wouldn't be a problem. But we have, you can see up here, it says that they are perpendicular to the y-axis. If it had been the x-axis, let me use green here, the slices would look like this, and you could just have a continuum of slices from the left over to the right, and everything would be great. Okay, but it didn't say that, so we have to get rid of those, and we need to put in slices that actually go the other way. So you can see I'm going to put in a dark line here. We're going to have slices up to that point, and then we're going to have slices, let me actually change colors here, in that also go like this. So we can see there are two different regions of slices that we need to account for. So let us figure out what the volume would be for each region. Okay, so first of all, we know that we're dealing with square cross sections. So it's always good to write what a volume element would be. So that would be s squared times, in this case, since they are horizontal slices, it will be delta y. So let's go to region 1. We'll do the red region first, and that will be region 1. This will be pretty easy because delta v, let me just write out the element again. S, since we're going horizontally, has to be from the right minus the left. Okay, so the right side, given the numbers that we have here, we went from x equals 1 out to x equals 2. The right side is always at 2, and the left side is always at 1. So the S value is simply 1. So for region 1, we can say delta V is equal to S squared, which is 1, times delta Y. So in region 1, we could set up a volume integral. Get rid of the keyboard, where volume is equal to the integral from, you can see for this region, we start down at y equals 0, but we have this point right here that is 1, 1. So we go up to y equals 1, and we're going to integrate 1 dy. Sometimes you don't write the 1. Writing the 1 is optional. So the antiderivative of that is simply y. We're going to evaluate that from 0 to 1. And so the answer is just 1. Okay, now that's the volume of the red region. We have to do the green region separately. So let me switch my pen over to green. For the green region, this is going to be a little bit more complicated. Call this, let me do this over here, region 2. We have to write delta V equals S squared delta Y again. S again will be the right minus the left. And so the right side is still at x equals 2. The complicated part of this is that the left side, you look at the left sides here, they keep bumping into the curve. Now, because we're working with delta y, we need to rewrite this curve, which was y equals x squared, we need to rewrite it as x equals the square root of y. So if we turn that around, we'll end up going we'll have minus the square root of y for the left side. Now let's just double check that this works. So let's put in a couple y values and some s values just to make sure that this is working out. So when y is 1, that would be the bottom of the green region, we end up with an s value of 2 minus 1, which is 1. When we get to the top of the region, that would be up here at the point 2, 4. If I put in a y value of 4, I end up with 2 minus 2, which is 0. So those check out nicely. They give us the right side lengths for our squares as we look at the two extremes of the region in terms of the y values. So let's continue along. So we now have a legitimate expression for s. Back to my green pen. And so we can write what the volume integral is. Volume is equal to the integral. Now y is starting at 1 and going up to 4. We need to square the s, so it's 2 minus the square root of y, and we're going to have to square it, and we'll integrate that with respect to y. Now we could do this by hand. We could expand the quantity 2 minus the square root of y squared and put in all of the terms, but I'm just going to pause the video and evaluate that on my calculator. When I put that into my calculator, I ended up with 1.33, which would be exactly 4/3 if I want an exact answer, but I'll use the decimal answer for now. And just one quick helpful hint, when you're using your calculator, you'll probably find that it's quicker, even though the variable is y, to just enter the integral from, so on the calculator, if you simply do the integral from 1 to 4 of 2 minus the square root of x with respect to x, its value will be exactly the same because the name of the variable doesn't really matter. It's what we're doing with it. So we would end up with the same value if we do it either way. So it's just faster in your calculator since your variable button will automatically give you x to do that. But you could always use the alphabet and type in y instead. So here we have it. We have the region added up in two different parts. And so if we wanted to get the volume, we'd have to get that the volume total is equal to 1 plus 1.33, which will be 2.33. So why did we have to use two different subintervals? Because if we look right here, when we're below the black line I just put in, the right-hand side always hits 2, and the right-hand side of the squares would always hit x equals 1. But when we're above that line, the right-hand side will continue to hit x equals 2, but the left-hand side keeps hitting new values given by x equals the square root of y. So we need to rewrite that as a separate integral.